Well, welcome back. And today we begin a new chapter since we finished chapter 5 in the last lecture. So hopefully you're keeping up. Remember the questions for chapter 5 are due Tuesday. That would be April 6th. And this chapter here marks a switching gears a little bit. We start boring down, so to speak, into the structure of atoms. We've seen in general, in a very general term, what atoms look like. Essentially, what we've seen so far, or the most advanced level we've gotten to so far, is known as the Bohr model of the atom. That's where the model of the atom stood circa 1913, like 108 years ago, which was actually pretty advanced. That's pretty close to the way that it really is, and pretty close to the state-of-the-art view of the atom today, but it's not quite there. So what we're kind of leading up to toward the middle of this chapter will be the Bohr model of the atom, where you have the small, heavy, relatively speaking, nucleus at the center. That's where the protons and neutrons are. Although in Bohr's time, they didn't know about neutrons, but they knew that the nucleus was small and heavy, and that's where the positive charges in the atom were. And you also have very small, very light electrons circling around the nucleus, as sort of analogous to planets circling around the sun. And they have orbits, which in the Bohr model are well defined. And it turns out that each orbit or each distance of an electron from the nucleus has a certain amount of energy associated with it. So so electrons in different orbits, even within the same atom, can have different energies. So that's kind of where we left off. Sort of working our way back to that, and then on to more advanced things like quantum mechanics. We have the chapter electronic structure and periodic properties of the elements. You might think that that's kind of a strange thing to put together, electronic structure of individual atoms and the periodic table. But actually, as I've mentioned before, the periodic table was set up based on grouping elements together that have similar properties. And it turns out that those elements have similar properties because they have similar arrangements of electrons within their atoms. So it turns out that electron or electronic structure is directly related to the periodic properties of the element, or the way that the periodic table was set up back in 1870. And that's what I'm saying here. Chemical properties of the elements and the arrangement of the periodic table are both based on the arrangement of electrons within the atoms of the elements. So similar arrangement of electrons will mean similar properties, even for different elements. If they have similar arrangements of electrons, their properties won't be the same, but they'll be similar. And this leads them to be grouped together in the columns in the periodic table, at least for the main groups or the A groups. That's true. But first, some background information. We're sort of working our way to this, because we have to have some background information in order to understand how we came to our current understanding of the structure of electrons within an atom and how they relate to chemical properties. This isn't something that just fell out of the sky on top of scientists' heads, like the apple on Newton's head, supposedly, but it was something that scientists led up to through a series of investigations over decades, sort of each successive scientist refining the ideas of the scientists who came before. And so the first thing we have to get into is the idea of electromagnetic radiation, or electromagnetic energy, as the book likes to call it. This is a background because this electromagnetic radiation was instrumental in actually devising not only the structure of the atoms, but why that structure is the way it is and why it affects chemical properties so much. So electromagnetic radiation, which is a real pain in the butt to keep writing out over and over again. So you're going to see the abbreviation EMR quite often in my notes anyway, and that means electromagnetic radiation. So just be warned about that. Electromagnetic radiation is a form of energy that travels through space in the form of waves. And those waves are able to transport that energy from one place to another. Now, electromagnetic radiation takes in more than what you probably think of as radiation. When most people hear the word radiation, they think of nuclear radiation, which is a form of electromagnetic radiation, but it's not the only one. Electromagnetic radiation takes in a broad range of types of energy that travel as waves, and that can include anything from radio and TV signals that have such low energy that we are being constantly bombarded by radio and TV signals from all of the different radio and TV stations in town. They broadcast their signals out, and they basically spread their signals everywhere. So we are literally bathed in radio and TV signals 24/7, and the energy of those is so low that we don't even know it. We don't notice it. There are no long-term consequences or anything like that. Light, visible light, is a form of electromagnetic radiation also. Ultraviolet and infrared light are also types of electromagnetic radiation, and also things like X-rays. When you get into UV and X-rays, you're getting into the level where the electromagnetic radiation has enough energy that it actually can cause harm, and we actually do have to limit our exposure. But for things like radio and TV or visible light or infrared, no problem, very low energy. And they're all around us all the time, and there are no negative consequences. We'll get to that electromagnetic spectrum, which is the sort of the sum total of all of the different forms of electromagnetic radiation a little bit later. So we'll go into that in more detail in a while. Also, we want to think about, at least in advance, the idea of wave-particle duality. We'll get into that in more detail in the future also, but just sort of to keep in mind that everything that exists physically has particles of waves and properties of waves and properties of particles, that is physical matter, to some extent. And the extent to which various physical objects exhibit such properties really depends basically on their size. So if you look at something like electromagnetic radiation, which is kind of on the borderline of whether it exists physically or not, the particle associated with electromagnetic radiation is known as a photon. And although that is considered to be something that physically exists, it is also at the same time considered to have no mass, which is kind of contradictory because we define matter as things that have mass. So to have a piece of matter that doesn't have any mass would seem to violate the rules of physics. But this is the kind of thing that you run into when you start studying quantum mechanics. Things get really weird really fast when you get down to a small enough level. And electromagnetic radiation happens to be on that level. For electromagnetic radiation, the wave properties are much more significant than the particle-related properties. But there are particle-related properties associated with electromagnetic radiation, as we'll see in a little while. For instance, light exerts a certain pressure on anything that it falls on. The light that I have here lighting up this paper is exerting a small amount of pressure on that paper. If I turn the light off or block it, the pressure goes down. It's not enough to measure with conventional instruments, but there is some pressure there. And if light consisted of purely a wave and not a particle, then it would not be able to exert pressure. And so there has to be some particle associated with light. And the same is true of other types of electromagnetic radiation. If you move up from the level of photons up to electrons, which as small as they are, they're quite a bit bigger than photons. It turns out for electrons, the wave properties and the particle properties are about equally significant. And that will come into play when we try to figure out the detailed structure of the atom, particularly with respect to the arrangement of the electrons in an atom. The wave properties will play a big part in how that was how the arrangement of electrons was determined. When you get up into larger items, like say anything from the size of a molecule on up, including us, then the particle properties obviously outweigh the wave properties by a huge margin. But nonetheless, a person walking down a hallway does have wave properties as well as particle properties. Thus, the particle properties are a whole lot more noticeable and a whole lot more significant. So everything has wave properties and particle properties at the same time. It's just a question of which are more significant. And for electrons, they're about the same in terms of significance. Now, getting into waves. A wave is just an oscillating periodic motion around a central position, something like I've drawn here. Forgive my sort of crippled artistic ability, but that's, you get the idea anyway. It goes up and down around a central point, which is the dotted line here. Waves, as I mentioned a moment ago, are capable of transporting energy from place to place. Some of these waves are physical, also known as mechanical waves. And that mechanical waves would include things like sound, which travels in waves. And that consists of basically particles of air, that is, molecules of oxygen and nitrogen and carbon dioxide and water vapor and whatever else happens to be in the air, banging against each other in succession from one place to another. There are also water waves. You drop a stone in calm water, you can see the ripples moving out from the stone. Those are waves, and they have properties that are governed by wave equations, the same kinds of equations that we can use for things like sound. And also a guitar string is an example of a wave. That's what's known as a standing wave, because the wave doesn't actually move from one place to another, but it does. But the string does oscillate back and forth around a middling position. So it is a wave. And with this kind of wave, you basically transfer kinetic energy from one place to another through collisions of matter. But the particles basically stay in place. With sound, one oxygen molecule bangs into another oxygen molecule, and on and on and on with successive collisions, and that can go on over a long distance. But each oxygen molecule only moves a little bit in that process, and it's the same with the water molecules in a water wave. And in the guitar, the particles actually stay completely in place, except for their oscillation up and down or back and forth. They don't move along the length of the string at all. Some waves, on the other hand, are not physical. And then with that, we're basically talking about electrical and magnetic fields, or in other words, electromagnetic radiation. So that's an example of a wave that's, well, even though the photon physically exists, for the most part, the wave properties are much more significant. So we consider that on the whole, electromagnetic radiation is something that doesn't physically exist. It's a form of energy, and except for the few properties that depend on the photon, it's safe, it's normal to say that electromagnetic radiation doesn't exist physically. It's just energy. Okay, moving on. For electromagnetic radiation, now, when we're talking about sound has a certain speed that it travels through air. Water waves can travel at a variety of different speeds, depending on how much energy is involved. And as it turns out, electromagnetic radiation, all of those waves travel at the same speed, no matter what type of electromagnetic radiation you're talking about, whether it's radio waves or visible light or X-rays, all of those waves travel at the same speed. And this is colloquially known as the speed of light, or C as an abbreviation, lowercase c. And that number is 2.998, which we often just round off to 3 times 10 to the 8th meters per second. That's really, really fast, much faster than the speed of sound, for instance. You've probably noticed, well, a good example of that is lightning. when you see the flash of lightning, what you're seeing is the light rays, the waves of light traveling from the lightning to your eye, which occurs at a certain speed. And the thunder is a series of sound waves, which travel from the spot where the lightning struck to your ears, and they do it at a much slower rate than the light travels. And that's why the thunder always comes after the lightning. The thunder is caused by the superheating of the air by the lightning, which is essentially a bolt of electricity at extremely high temperatures, and it superheats the air around it. And that air quickly expands because gases expand a lot when they heat up. And so the air particles, oxygen, nitrogen, and the other stuff in the air, they move apart from each other really fast. And that has a knock-on effect where they hit particles that are next to them, and they hit particles next to them, and so on until it reaches your ear. And that is what we hear as thunder. And that energy dissipates over distance because of the energy required just for knock one molecule into another in the air. And so that's why the further away you are from a lightning strike, the quieter the thunder tends to be. That happens, the point here is that happens at a much slower rate than the light travels, and that's why the thunder always comes after the lightning, or at least that's our perception of it. The speed of light is 3 times 10 to the 8th meters per second in a vacuum, but actually it's about the same in air, but it can actually be significantly slower in other media. So the speed of light actually depends on what the light is passing through. If it's passing through a vacuum, which is essentially nothing, then it'll be 3 times 10 to the 8th meters per second. If it's traveling through air, which when it comes right down to it is practically nothing, then it's also 3 times 10 to the 8th meters per second. But if it's traveling through something like water or glass, it'll be quite a bit slower. And so the speed of light is a constant depending on what it's traveling through. So the speed of light through glass will always be the same for that type of glass, although there are different types of glass, and each one has a certain speed of light within it. For water, if it's pure water, then really temperature would be the only thing that would affect the speed of light in the water. But then the speed of light through pure water at a given temperature should always be the same. But the speed of light that we're going to use will be 3 times 10 to the 8th meters per second. The book likes to use 2.998, but as far as I'm concerned, 3 times 10 to the 8th is close enough for our purposes. So you can use that if you like. Okay, so some properties of waves, because we want to investigate these things scientifically, so that calls for a certain amount of detail. So we better know, what are the basic properties of waves? What are they like, and how do they behave? Well, all waves have what's known as a wavelength. A wavelength is just the distance from one part of a wave to the corresponding part of the next wave. So, and it's usually measured either from peak to peak or trough to trough. The trough is the minimum between the peaks. So for a wavelength, you'd either measure from the peak of one wave to the peak of the next, or the trough of one wave to the trough of the next. The units for wavelength would be units of distance. And since that's what it is, it's a distance. You can use any units of distance you want. You could use inches or miles or nanometers or any other measure of distance that you can think of. But there are certain customary units that we use in science, and to some extent, the customary unit you would use for the wavelength of a type of electromagnetic radiation would depend on what type of electromagnetic radiation it is, because we usually shoot for units that give us a reasonable number to go along with the unit. So for instance, if you're dealing with visible light, measuring things in nanometers usually gives you a reasonable number, something in the hundreds, usually between about 400 and 700. And so we tend to use nanometers for visible light. On the other hand, all of the equations that we commonly use for dealing with electromagnetic radiation require units of meters for wavelengths. So if you're given a wavelength in something else, like say nanometers, then you would need to change it to meters before you could put it in an equation. The ranges of wavelengths for electromagnetic radiation cover quite a wide span. They can go anywhere from several kilometers or miles, basically, for radio and TV waves, down to picometers for X-rays, or sorry, gamma rays. That little symbol there is the Greek letter gamma, the lowercase gamma. Gamma rays are the highest energy forms of electromagnetic radiation, and radio waves and TV waves are the lowest energy form of electromagnetic radiation. So what you can tell right away is that wavelength is basically inversely proportional to the energy for electromagnetic radiation, because really big or long wavelengths on the order of miles would correspond to really low energy, and really small or short wavelengths on the order of picometers would correspond to really high energy, like gamma rays. There's also frequency. All waves have this property, as long as they're moving anyway. Standing wave for a guitar string, actually a string wouldn't have a frequency linearly, but it would have a frequency up and down. This frequency is defined as the number of complete waves. A complete wave would be a peak and a trough. So basically that pass a given point every second. And so the units that we normally use for frequency would be waves per second, or sometimes called cycles per second. A full wave, peak and trough is also called a cycle. So cycles per second, or just seconds to the -1, because we don't actually write the word wave or cycle. So waves per second or cycles per second is treated as if it's just something per second. And that's what s to the -1 means. It means 1/seconds, or something that's unnamed, per second. This is also known as a hertz, or Hz. So 1 hertz is 1 inverse second, or 1 per second, or 1 wave per second would be 1 hertz. The values for frequency are usually large. Even for the longest wavelengths, the values for frequency will be quite large, because we're talking about individual waves passing a given point every second for something that's moving at the speed of light. So even if those waves are really long and stretched out, there's still going to be quite a few of them traveling past a given point every second. And so hertz tends to be used a lot with metric prefixes. So like kilohertz, KHC, that would be 1,000 hertz, or 1,000 per second, or 1,000 inverse seconds. A megahertz would be 10 to the 6th, or a million hertz, or a million waves per second. So like if you listening to a radio station with a frequency of 91.3 megahertz, that would mean that 91.3 million waves are passing into your antenna every second. And that's a lot of waves. But even though radio waves have relatively long wavelengths, you still get a lot of them per second. And even gigahertz for a lot of things. Gigahertz would be 10 to the 9th, or a billion waves per second. And waves also have a property known as amplitude. Amplitude is the distance from the minimum or the maximum, that is the peak or the trough, to the center point. So you draw a line right down the middle of the wave, and the distance from there to the top of the peak would be an amplitude, or from there to the bottom of a trough, that would also be amplitude. And normally the amplitudes measured either way would be the same. So the distance, because this is the center point, so by definition the center point is in the middle, and so therefore the distance from the center point to the top should be the same as the distance from the center point to the bottom, because it's the center, right? So basically the amplitude is just half of the distance from the, it's the distance from the center point to the peak or the trough, or in other words, half of the height from the trough to the peak. So that would be, all the way. The amplitude is related to brightness if you're talking about light, or loudness if you're talking about sound. Okay, and actually AM radio signals work by varying the amplitude over time. That's how you get the sound. The amplitude will increase or decrease. And in fact, AM stands for amplitude modulation. In other words, changing the amplitude. FM, on the other hand, changes the frequency of the waves for the signal, which and FM actually stands for frequency modulation. Okay, so for any given electromagnetic wave, we have a certain relationship here. The wavelength is inversely proportional to the frequency. Oh, yeah, I forgot to mention as I was going over them. The wavelength, the symbol for wavelength is lambda. This is the lowercase Greek letter lambda. They'd use so many L's for so many other things that we had to go to Greek to find a symbol that we hadn't used before. And lambda in Greek is the equivalent of L, presumably standing for length in this case. And that is the symbol of wavelength. The symbol of frequency is this here, which is kind of obscured. It looks kind of like a fancy V leaning a little bit to the right. And that is the Greek letter nu, which is, it's a lowercase nu. The uppercase nu looks just like a capital N. And in this case, it is the equivalent of the English N. And presumably they chose it here to represent number, N for number, or number of waves per second. And that is the symbol for frequency. Okay, so as it turns out, wavelength is inversely proportional to frequency. As wavelength goes up, frequency goes down, and vice versa. Or you could say frequency is inversely proportional to wavelength. Both of these mean the same thing. So if you have two electromagnetic waves and one of them has double the wavelength, it'll have half the frequency, and vice versa. And also what that means is probably if you take wavelength times frequency for any given electromagnetic wave, you should end up getting the same number every time. And in fact, you do. Wavelength times frequency for any given type of electromagnetic radiation will give you the speed of light. Okay. That's because if you look at the if you look at the units, wavelength would have units of meters, and frequency has units of seconds to the -1. So wavelength times frequency in terms of units would be meters times seconds to the -1, or in other words, meters per second. So actually, you get meters per second as the unit, and the numbers for any corresponding wavelength and frequency will give you 3 times 10 to the 8th. And since we already know what the speed of light is, 3 times 10 to the 8th, we often use this equation rearranged in order to solve for wavelength or frequency. So if you know wavelength and frequency, you can find wavelength. Wavelength is just c, speed of light, divided by frequency. And frequency is just speed of light divided by wavelength. Something to keep in mind, though, is you have to keep the units consistent. So if the speed of light you're using is in meters per second, then wavelength has to be in meters. And that's the important one. That's the one that you might actually be given something else. So wavelength has to be in meters, and frequency has to be in hertz, or inverse seconds, or seconds to the -1. frequencies usually will be given to you in units of hertz or seconds to the -1, but wavelength a lot of times will be given to you in something other than meters. So watch out for that. All right, so the energy, as it turns out, the energy of electromagnetic radiation is directly proportional to the frequency. So higher frequency means higher energy. And it's inversely proportional to the wavelength. So longer wavelength or bigger wavelength means lower energy, like radio waves. And shorter wavelength or smaller wavelength, in other words, means higher energy, like X-rays or gamma rays. Okay, so that's what this means here. And I see we're at about 30 minutes, so I'm going to cut off part A here. But when we come back, we will look at the electromagnetic spectrum. And that'll be interesting to see them all together and all the variation in energies and types of electromagnetic radiation. So I'll be right back.